students, in this video we will see the calculation of crystal field stabilization energy, and this we are going to see for octahedral complexes. Now crystal field stabilization energy, which is abbreviated as CFSE, as the name suggests, it is related to the stabilization, that is the stability of a complex. So it gives us an idea of the stability of the complex, and there are ways of calculating this crystal field stabilization energy, that is CFSE, for octahedral complexes, and we will see it in two parts. First, we will see that if the complex is formed by a strong ligand. Now, in the previous video, we saw that if the ligand is strong, then crystal field splitting is more. That is, the gap between T2G and EG is very high. And we know that this gap is called, this energy gap is arbitrarily taken to be 10 dq. So this splitting is more when the ligand is strong, and when the ligand is weak, then these orbitals are closer, that is, the energy gap is less. So in the case of strong ligands, if you have to fill the electrons in the d orbitals, then how are the electrons filled? This T2G is 4 dq less than this original energy level, and EG is 6 dq higher than this energy level, which is the original level of the degenerate orbitals. So when the electron gets filled, in the case of a strong ligand, when electron gets filled in the central metal d orbitals, then electrons are filled in the T2G first. So first electron, second electron, third electron, and since this gap is higher, so instead of going to EG, they prefer to get paired up in EG. We saw it in the previous video that pairing energy is greater than 10 dq. 10 dq is greater than pairing energy. That is, they will try to get paired up rather than going to EG. And when this is completely filled, then they go to EG, and finally they get paired up in EG also. This we had already seen in the previous video. Now what you have to remember for calculation of stabilization energy, that if any electron is being filled in T2G, for one electron which is being filled in T2G, this energy level, the level of T2G is 4 dq below. That is, the CFSE calculation will involve minus 4 dq for one electron to be filled in T2G. That is, if there is system D1, so one electron will be filled in T2G. So the crystal field splitting energy will be minus 4 dq. So minus 4 dq will be for one electron filled in T2G, and same way, if electron is filled in EG, then for each electron which is filled in EG, the energy will be taken as plus 6 dq. Why? Because this is higher by 6 dq from this energy level. So this assumption will be followed here, that for one electron filled in T2G, you will keep the energy, you will calculate it using minus 4 dq. Why? Because it is below this level by 4 dq. And if one electron is there in EG, then the 6 dq is above this level, so you will calculate the energy by taking plus 6 dq. So keeping this in mind, we will fill up the electrons in the case of a strong ligand, and we will calculate the crystal field stabilization energy. So let us see the strong ligand first. So in the case of a strong ligand, D configuration can be D1, D2, D3 to D10. So if there is the configuration D1 for any central metal, then in T2G and EG, remember a strong ligand means this gap is higher and they try to get paired up. That is when T2G will be singly filled, then they will be paired up in T2G only because this gap is higher. So if one electron is to be filled, then it will be filled in T2G. And how will you calculate the CFSE? The calculation of CFSE is very simple here because one electron is filled in T2G. So for one electron in T2G, we have to take minus 4 dq. So the crystal field stabilization energy will be simply minus 4 dq. For one electron, minus 4 dq for T2G, and if the electron goes in EG, then it will be plus 6 dq. Now, if there are two electrons in D, then first electron, second electron. So CFSE will be minus 4 dq for 1. So 2 will have minus 8 dq. The crystal field stabilization energy here will be minus 8 dq. Why? Because minus 4, it will be minus 8. Same way, if the configuration is D3, then third electron will again come in T2G only, and it will be minus 4 dq for 1. So there are 3 such electrons, so it will be minus 12 dq. Now, when the fourth electron is filled, then since it is a strong ligand, it will get paired up here and will not go to EG. So fourth electron will come here. See, it got paired up in T2G. 1, 2, 3, 4. Now total number of electrons are 4 and they all are in T2G. Therefore, the energy will be minus 4 for one electron, and there are 4 electrons in T2G. So minus 4 into 4 is minus 16 dq plus 1p. What is this 1p for? Because we have one pair. If you will have two pairs, then 2p will be added, 3p will be added if 3 pairs. So one pair is there. So in minus 16 dq, 1p will be added. Now when we have D5, now 1, 2, 3, 4 and 5. That is minus 4 for 1 and there are 5 such electrons in T2G. So it will be minus 20 dq. And since 2 pairs are there, it will be plus 2p. Exactly in the same way, D6 will have 1, 2, 3, 4, 5 and 6. Minus 4 for 1 in T2G. For one electron, minus 4 dq, and there are 1, 2, 3, 4, 5, 6 such electrons. So minus 4 into 6 is minus 24 dq, and since we have 3 pairs, it will be plus 3p. Now T2G is completely filled. Now if we have 7 electrons, then 1, 2, 3, 4, 5, 6 will be there in T2G, and 7th will go in EG. Right? So for this, for each of these electrons, we have minus 4 dq, and for EG we have plus 6 dq. So the total energy will be here. Total energy will be here minus 4 for T2G, and we have 6 such electrons. So minus 4 into 6 plus this will be 6 dq. So minus 4 into 6 plus 6 will be equal to minus 24 plus 6, that is minus 18 dq, and total pairs are 3 only, so plus 3p. Right, so minus 4 into 6, this is 42G, and 1 is in EG, so plus 6. So minus 24 plus 6, that is minus 18 dq, and 3 pairs are there, so 3 dp. Now D8 is the configuration, so 1, 2, 3, 4, 5, 6, 7 and 8. So this will have minus 4 into 6, total 6 electrons in T2G, and 1 is having minus 4. So minus 4 into 6 plus this will be 6 into 2. Why? Because plus 6 is for 1 electron. So for 2 electrons it will be plus 6 into 2. So it will be minus 24 plus 12, that is minus 12 with dq. And number of pairs are still 3. So plus 3p. Right? Same way in D9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So total for this it will be minus 4 into 6 plus it will be 3 electrons. So 6 into 3. So it will be minus 24 plus 18, that is minus 6 dq. And total pairs are 1, 2, 3, 4. So plus 4p. And for D10 we will have filling like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So minus 4 into 6 plus, for this it is plus 6 and there are 4. So this is minus 24 plus 24, that is 0 dq. And the pairs are 1, 2, 3, 4, 5 plus 5p. So the total energies are for D1 minus 4 dq, for D2 minus 8 dq, for D3 minus 12 dq, for D4 minus 16 dq plus 1p. Why? Because pairing has started. And there are 2 pairs, so minus 20 dq plus 2p. 3 pairs, minus 24 dq plus 3p. Now here minus 18 dq plus 3p. For this minus 12 dq plus 3p. For this minus 6 dq plus 4p. And for D10 we have 0 dq and 5p because the total pairs are 5. This way we calculate CFSE for a strong ligand, and let us now see the calculation of CFSE in the case of weak ligands. So the configurations can be D1. We will fill the electrons in T2G and EG, but you know this gap is less because this is a weak ligand. So you will be filling like 1, 2, 3, then we will go here 4, 5. Why? Because here pairing energy is more. We saw in the previous video. So filling will be first electron is here. We will follow the same way of calculation here. We will calculate CFSE here. In T2G we are filling just 1 electron in T2G in D1 configuration. Therefore it will be minus 4 dq. Now when you fill the second electron, you fill it here and it will be minus 4 into 2, that is minus 8 dq. And when you fill the third electron, you will again fill in T2G only. So minus 4 into 3, that is minus 12 dq. Now when the fourth electron comes, if it's a weak ligand, so gap is low, so it will prefer to go to EG. Had it been a strong ligand, then it would have got paired up here only. See, in the strong ligand, the fourth electron did not go to EG. It got paired up here only because pairing energy was less here. And here the pairing energy is more and this 10 dq is smaller. So it will prefer to go to EG. When 1, 1, 1 is filled here, then fourth will prefer to go to EG. So when we have to fill the fourth electron, we will not do pairing. We will bring this fourth electron in EG. And the calculation will be, here we have 3 electrons, so minus 4 into 3 plus we have 1 for 6. Plus 6 for EG, minus 4 for T2G. So it will be minus 12 plus 6, that is minus 6 dq. Right? Now, fifth electron will be filled in EG again, 1, 2, 3, 4, 5. So total electrons in T2G are 3. So minus 4 into 3. And there are 2 into 6. For this it is plus 6 into 2. So it will be minus 12 plus 12, that is 0 dq. The CFSE will be 0 dq here. Now for D6, 1, 2, 3, 4, 5. Now all are singly occupied. Now pairing will start here. So total 6 electrons. So 1, 2, 3, 4 are in T2G. So minus 4 into 4. Plus 2 are in EG. So 2 into 6. And it will be minus 16 plus 12. That is minus 4 dq. And don't forget to add 1p, because 1 pair is also there. So minus 4 into 4 is minus 16 and 2 into 6 is 12. So it is minus 4 dq plus 1p. Similarly, D7 will have 1, 2, 3, 4, 5. First you will fill in T2G and then you will fill in EG. And when 1, 1 will be filled, then 6th electron, 7th electron. So you will have minus 4, 1, 2, 3, 4, 5 electrons are here for minus 4. So minus 4 into 5 plus 2 electrons for 6. That is minus 20 plus 12. That is minus 8 dq, and the total pairs are 2. One pair, second pair. So plus 2 dp, plus 2p. Now if we have D8, so filling will be 1, 2, 3, 4, 5, 6, 7, 8. So minus 4 into 6 plus 2 into 6. That is minus 24 plus 12. That is minus 12 dq, and total pairs are 3. So 3p. Right. Now these are the final energies. And for D9, now T2G is completely filled. So for D9 you will have 1, 2, 3, 4, 5, 6, 7, 8, 9. So total electrons here will be minus 6 electrons in T2G. So minus 4 into 6 plus 3 electrons in EG. So 3 into 6. That is minus 24 plus 18. That is minus 6 dq, and total pairs are 4. So plus 4p. This is the final energy. And for last D10, it will be filling will be like 1, 2, 3, 4, 5. You can see that when the ligand is weak, then they try to remain unpaired. So there is high spin. And when all are singly occupied, then pairing start. So it will be 10 electrons completely filled. So minus 4 ke 6 electrons, or 1, 2, 3, 4 electrons will have plus 6 dq. So it will be minus 24 plus 24, that is 0 dq, and total pairs are 1, 2, 3, 4, 5 plus 5p. This way we calculate crystal field stabilization energy. You can be given any question to calculate like this. Calculate the CFSE for say the complex CuNH3 whole 4 SO4. Now remember, NH3 is a strong ligand. So when NH3 is a strong ligand, then the filling will be taking place like this: first, second, third, एंड स्ट्रॉन्ग लिगैंड में ये गैप ज़्यादा है हमारा, तो पेयरिंग हो जाएगी 4, 5, 6 and then 7, 8, 9, 10. So here copper will have the oxidation number +2 because sulfate has -2, so copper will have +2. Copper in the ground state has the configuration 3D10 4s1. So copper +2 will have the configuration 3D9. That is, we have to calculate CFSE for 3D9 and in the case of a strong ligand. So how do you fill electrons in T2G and EG? A strong ligand 1, 2, 3, 4, 5, 6, 7, 8, 9. पहले हमने T2G पूरा भर लिया, फिर EG क्योंकि ये गैप ज़्यादा था. सो CFSE कितना हो जाएगा? 6 इलेक्ट्रॉन्स with -4 plus 3 electrons with +6. That is -24 plus 18. That is -6 dq. And total pairs are 4. So +4p. This is your answer. This way questions are given that strong or weak. You should know that the ligand is a strong or weak. Then find out the configuration of the metal, central metal. Then oxidation state of copper here was +2. So +2 means 3D10 4s1 में से 2 और निकाल लिए, तो एक ये गया और एक इसमें से गया. So 3D9 और स्ट्रॉन्ग लिगैंड को ध्यान में रख के हमने फिलिंग कर ली. और अगर यही हमारा होता, suppose the configuration is coming say D5 and it is a weak ligand, then how do you fill? In T2G and EG, weak ligand में this gap is low, so first, second, third it goes here, fourth, fifth. And a strong ligand में how does it fill? 1, 2, 3. Now gap is more, so it gets paired up here. This is the difference, and accordingly we calculate crystal field stabilization energy, which gives us an idea for stability of the complex. That's all for this video. Thank you.